Good day, everybody. Today I want to look at the cardinality of the rational numbers and compare it to the cardinality of the positive integers. So first, it might be well known that even though it seems like there's more total integers, if you count the negative and the positive, than there are positive integers, we can do a one-to-one correspondence, and so we say they have the same cardinality. So for example, if I want to map from the naturals into the integers, I can just, for every positive integer, if it's even, I'll send it to half that number. And if it's odd, I'll send it to, well, subtract 1. And so from odd, if you subtract 1, then it'll be even. Then divide by 2, but then take the negative of that. Okay, so every natural number gets sent to an integer, and in fact, every integer. So we say it's 1-to-1 and onto the integers. And if it's 1-to-1 and onto, then it's invertible. And here's the inverse. If you start with an integer, negative or positive, then I can map that to the positive integers just by, if it's already positive, just double it. And if it's not positive, then do 1 minus double it. So for example, if it's 0, then it gets sent to 1. If it were at -1, it gets sent to 3. If it were at -2, that would get sent to 5, and so on. So it'll get sent to all the odds, and all the positive integers got sent to the even integers, right? So 1 got sent to 2, 2 got sent to 4, 3 got sent to 6. So that will map all the integers to the natural numbers. So in a way, I mean, if there's a 1-to-1 and onto function, we say they have the same cardinality. And we can kind of do the same with the integers and all rational numbers. At first, that might seem surprising. We can think of some maps from the positive integers to the rationals that obviously don't cover the rationals. If I just let f of n equal n, that's not going to work, although that wouldn't have worked up above either. And we saw, there are as many positive integers as there are total integers. So f of n equals n doesn't work. F of n equals 1 over n doesn't work. So I'm mapping into the rationals, but obviously not onto. Before we try and get one that's 1-to-1 and onto, let's go the other direction. So it might be surprising. I can map the rationals into the positive integers, and it'll be 1-to-1, and again, not onto. And so for every rational number, and I'm including negatives, and so the rational can be anything, map it to essentially 3 to the numerator, but I want it to be absolute value, because if p were negative, I don't want 3 to the -4 power or something. So 3 to the absolute value of p, 5 to the q, and then to distinguish between positive and negative, I have 2 to the sine of p plus 1. The sine function is just 1 if x is positive. It's -1 if x is negative, and it's 0 if x is 0. So that function will be 1-to-1, but not onto. And let's just look at some values here. So g of 0 gets mapped to the sine of 0 is 0. So 2 to the 0 plus 1. So that'll be 2. The numerator is 0, so 3 to the 0, that'll be 1. And then 5 to the 1 power. So in the end, that's just 2 times 5, or 10. And now every other number will either get mapped to an odd number or an even that's actually divisible by 4. Because the only time we have 2 to the 1 is right here. Otherwise, it'll be 2 to the 0 or 2 to the 2. So for example, I'll look at some integers first. So the integers, 2 to we have to think of 1 as 1 divided by 1. So if it's positive, it gets mapped to 2 to the 1 plus 1, so 4, 2 squared. 3 to the 1, 5 to the 1, that's 15 times 4. And you have negative 1, the sign is negative 1, so that would be 2 to the 0 times 3 to the 1 times 5 to the 1, so 15. G of 2, that's positive, so 2 to the sine of 2 is 1 plus 1. 3 to the 2, 5 to the 1. So 9 times 5, 45 times 4, 180. And you have negative 2. The only difference if I go from positive to negative is this leading 1 goes to negative 1. So it becomes 2 to the 0. So this will just be 45. To say G of 6, my last integer, positive and negative, but so 2 to the sine plus 1, so 2 to the 1 plus 1, 3 to the 6, 5 to the 1, did on the calculator of course, and G of negative 6 over 1 would be 2 to the negative 1 plus 1, 3 to the numerator in absolute value, 5 to the denominator. And you can do this for any fraction. 9/7, just to keep it somewhat small. If it's positive, I'm going to have 4. It'll be 2 to the 1 plus 1. If it's negative, it'll be 1. So just positive and negatives determined by whether it's odd or even, divisible by 4. And then 3 to the numerator, 5 to the denominator. And of course that's 3 to the numerator in absolute value. And one more here. I already did the positive one. I didn't do the negative here, but so the idea is no matter what fraction you give me, if it's in lowest terms, it'll be 3 to the numerator and 5 to the denominator. And that's unique, right? There's only once you have P over Q in lowest terms, then I can't get to this same number again. Maybe I'll look at the 9/7 one. So that there's no other way to get to this integer. Because this, the fundamental theorem of arithmetic, this number is factored uniquely in primes, and it would be factored as 2 squared times 3 to the 9th times 5 to the 7th. So that's the only way to get to that integer. And only this fraction will get sent to there. So every fraction will get sent to a unique integer. Now we're going to skip most integers. I mean, any integer that has a multiple of 7 or 11, etc. They're all skipped. So it's just a subset of the integers, but every fraction there is from negative infinity to infinity will get sent to this subset of the naturals. So we can go both directions. We can map the integers to a subset of the rationals and the rationals to a subset of the positive integers. And so they must have the same cardinality. To try and get a one-to-one function, I'll first look at the integers in 0, 1. So here I'm going to list them kind of in a special order. I've got all the integers in the interval from 0 to 1, which I have denominator 2, and then denominator 3, and then denominator 4, and then denominator 5, 6, 7, etc. And then you kind of want to just go in order here. So 1 over 2, we'll call that the first one. So 1 over 2 will get mapped to 1. 1 over 3 will get mapped to 2. 2 over 3 will get mapped to 3. That'll be the third one. So we've kind of got this order. Now there are repeats though. So 2 over 4 is 1/2. That's not in lowest terms. So I want to skip that. If I take out all the fractions that are repeats, it'll look like this. So this 1/2 will get mapped to 1, 1/3 will get mapped to 2, 2/3 will get mapped to 3, 1/4 will get mapped to 4, 3/4 will get mapped to 5, and then 1/5 to 6, and so on. And any fraction in the interval from 0 to 1, if you give it to me, I can find out where it would be in this list. You know, if I keep going forever, I'll get every fraction. So if you give me a fraction, I can find out where it would be in this list, and then I can tell you which integer it would be. I mean, kind of in theory. In practice, you know, if you give me, well, actually, I kind of have a formula for it, although let's look at that. So for the integers in 0, 1, it's going to be using Euler's phi function, which gives you all the integers which are relatively prime. So if I look at which fractions I took out, it's 2/4. So 2 and 4 are not relatively prime. So I took that one out. And then over here I took out 2, 6, 3, 6, 4, 6. So 2 and 6 are not relatively prime. 3 and 6 are not relatively prime. 4 and 6, in other words, they have a common factor, so they're not relatively prime. If you have a prime denominator, then every integer less than will be relatively prime. But for 8, 2/8, 4/8, 6/8, those are not in lowest terms. So I usually call it the phi function. Some call it the totient function. Yeah, phi function, there we go. So it just tells you how many integers are relatively prime to a given n. In other words, the GCD, the greatest common divisor of the two, is 1. It means it's relatively prime. So here's a table of the relatively prime. And if I look at it, then I can see. So there's one relatively prime number that's for 2. So phi of 2 is 1. Phi of 3 is 2. Phi of 4 is 2. Phi of 5 is 4. Phi of 6 is 2. Phi of 7 is 6. Because these 6 numbers are all relatively prime, these 6 numerators. Phi of 8 is 4. And notice after 1/2, they all come kind of symmetric. If you look, they'll add up to 5 if you go oppositely. Or they'll add up to the denominator, I should say. So 1 and 4, if the numerators add up to 5, 2 and 3. Or if I go, say, here at 10, 1 and 9, 3 and 7, etc. 14, 1 and 13, 3 and 11, 5 and 9. So they come in that symmetry. So it's always going to be even once you get above 2. So if that's the first, and then that's the second and the third, then you can see this function where I add up phi of m for all values less than my current denominator. Let's start with 5. So at 5, I want phi of 2 plus phi of 3 plus phi of 4. So that'd be 1 plus 2 plus 2. So I'm at 5. And then for p, I want to know, what number it came in. Maybe I'll look at, say, 5/8. So for 5/8, I need to add up phi of 2 plus phi of 3 plus phi of 4 plus phi of 5 plus phi of 6 plus phi of 7. And if you add them up, it's 1 plus 2 plus 2 plus 4 plus 2 plus 6. And that's 17. And then, so say if I have 5/8, then I need to go 17, 18, 19, 20. So 5 is the third integer that's relatively prime to 8. So 5/8 will be the 20th number. So I'm mapping every fraction to the positive integers. Every fraction in 0, 1. Right, so add those up, and then all relatively prime to q, less than or equal to q. If you want to look at every fraction, this will be for the positive fractions. You can make this list 1, 1/2, 1/3. So this is the same list as before, but now I've got, right, so here was the list before, but I stopped it so I didn't go bigger than 1. But if I want it bigger than 1, it looks like this. So 1, 1/2, 1/3, 1/4 forever, 2 over 1, 2 over 2, 2 over 3, etc. 3 over 1, etc. And so you can do this. So every positive fraction will be in this list somewhere, and we would be able to find out where if you give me the fraction first. But again, there's repeats. If I take out the repeats, it looks like this, and I'm not going to do the rule. But so now, again, there's the first, and you do sort of a diagonal thing. So 1 over 1, then 1 over 2, 2 over 1. And then I just like to circle back. 3 over 1, I have to skip that, 1 over 3. And then 1 over 4, 2 over 3, 3 over 2, 4 over 1. Then 5 over 1, skip, 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 1 over 5. 1 over 6, 2 over 5, 3 over 4, 4 over 3, 5 over 2, 6 over 1. And whatever number I'm at, hopefully I didn't mess up the diagonal, but that would be the way to map the rationals to the natural numbers, 1 to 1 and onto. And then if you want, so this would be the positive rationals actually, but the same way we can do you could do the negative rationals to the negative integers and then make that into just the positive, but I don't want to go through the details there. And so once you know the rationals are countable, anything that's countable has measure 0, you can always cover it in something with measure epsilon for any epsilon, no matter how small. Right, so you can do the union, I'll just do the rationals, that's the easiest, the union of all rationals, and then you center. So if p over q is your center, you subtract epsilon over 2 to the m plus 1, where p over q is the mth rational, plus epsilon over 2 to the m plus 1. So that's a interval centered at p over q, whose radius is 2 to the m plus 1, epsilon over 2 to the m plus 1, or whose diameter is epsilon over 2 to the m. And so the length, whoops, I put less than or equal to. I meant to do the measure of this, but that's okay. So the measure of this would be less than or equal to epsilon over 2 to the m. And if you sum that up from 1 to infinity, you get epsilon. So you can the measure of all these intervals, the lengths, some of the lengths can be made as small as you like. So it must have measures, because we say 0. Another way to do it would be, here I put mth rational, but you could use that function I had before, 2 to the value of that function. That's 2 to this g function. And so for every rational on the real line, you do the union, you epsilon over 2 to the g of that, and you get a unique power, positive integer, for every rational. And of course we skipped a bunch, so that'll be less than epsilon over 2 to the m. So it'll be less than epsilon for any epsilon. So the rationals have measure 0. They can be covered as small as we like. Epsilon could have been as small as we like. And lastly, the rationals are solutions to this degree 1 equation with integer coefficients. And if I change it to a1, a0, I like to have a positive in the front. It's not necessary, but it could be, if it's a solution to any equation, if you had a negative in the front, just multiply the whole thing by a negative, and then it'd be a positive. So without loss of generality, we can assume the leading coefficient is positive, but every other coefficient is just some integer. Then there's countable number of equations. with integer coefficients. So like there's countable number of quadratics. Each can have up to 2 solutions, and that's countable. And the union of countable union of countable is countable. So there's countable number of degree 2 solutions and countable number of degree 3 solutions. And basically, we call a number algebraic if it's a solution to an nth degree polynomial with integer coefficients. They're all countable, so algebraic numbers are countable. So that's all I wanted to say. Hope that gives you something to think about. And enjoy the rest of your day.